All right, this video is designed to help you understand how to sort of advance DeMoivre's theorem, a theorem we already have learned how to use to find the powers of complex numbers in order to also find roots of complex numbers. And we'll show you why we need to be able to do that, as well as give you a couple examples of finding those roots. So the first thing we want to remember how to do is how to use DeMoivre's theorem. So looking at a complex number like 3 plus 4i to the fifth, again, distributing 3 plus 4i times itself over and over and over again is a lot of work. So a better idea is to convert 3 plus 4i into a trig form complex number. So first thing we need to know is, what would the radius be? If we're thinking about that complex number on a graph, right, we'd be going 3 units to the right and 4 units up, and we want to know sort of what that distance from 0 is, or basically its absolute value. Well, r, remember, is the square root of your two components, your real component squared plus 4 squared, or your vertical component, thus giving you 5 for an r. Then we also want to find theta, the direction angle. We need to be able to find that angle, theta here. So theta will be the inverse tangent of b over a. Remember, inverse tangent of 4/3 being 0.9273. Then, using DeMoivre's theorem, remember we can say, well, hey, if r to the fifth CIS to the of 5 theta, so r to the fifth would be 5 to the fifth, cosine plus I sine of our angle, and notice we're just in radians, so that's perfectly fine. I'm just going to take 5 times that radian angle and get 4.6365. Then if we want to go back to standard form, we can actually find those numbers. So 5 to the fifth is 3125 times the cosine of 4.6365 will give you negative 1,875. 3125 times the sine of 4.6365 is 2,500. And don't forget that that's cosine plus I sine, so that second term has the I in it, and we've got our standard form number. So that's DeMoivre's theorem. Now, at the bottom of the screen here, we have to remember when we're solving polynomials, something that's already to a power, how do we find those solutions? How do we find all the possible answers? And remember that x squared equals 81. We're just going to take the square root on both sides, which is a great idea, but you have to remember one very important thing, and that's to say plus or minus. Remember, it has multiple answers. If you take the square root on both sides of an equation, we say plus or minus, and the square root of 81 is 9. So we get two possible solutions. And basically, we've chopped our full circle in half. We get one answer to start, half a circle away we get another answer, and then a half a circle away we would be right back to our initial answer. That same idea works for x to the fourth equals 16. X to the fourth minus 16 would equal 0. I could factor those two parts if I wanted to, and then find all possible solutions. So again, x squared minus 4 would have answers of 2 and negative 2. X squared plus 4, remember, if I subtract 4 and take the square root, is going to have answers of 2i and negative 2i. And again, if we plotted those on a complex plane, we'd have 2, negative 2, 2i, and negative 2i. And notice again how we've sort of chopped this into 90 degree, there we go, increments, but 4 sections. Same thing works for x to the third. Now that one's a little bit trickier, because x to the third, we would actually have to use a cubic formula, which we don't use very often as far as factoring goes, but it does work. If you remember way back when, we learned that x cubed minus 125, since that's really just 5 to the third, can be x minus 5 times x squared plus 10x plus 125. Now, you don't have to really remember that, because we'll show you another way to get these answers, but what that means is 5 will be one of my possible solutions, as well as the answers to the quadratic equation for 1, 10, 125, which are given down here as negative 5 halves plus 5i root 3 over 2, and negative 5 halves minus 5i root 3 over 2. If you take a good look at, again, where those would fall on a complex plane, graphing your real numbers from the left and right, and I, or your imaginary number, up and down, notice we chopped that perfect circle into 3 even sections. Now, what that means is we can take advantage of that circular idea in order to find our roots. And we can also take advantage of DeMoivre's theorem because powers and roots are very relatable. If we think about it, x to the n minus z, some sort of complex number, could also be rewritten as x equals if I add the z to the other side. So equal to z. and then take the nth root of z, or basically z to the 1/2 power, just like in DeMoivre's theorem, using our powers, then we can rewrite the nth root of z as the nth root of r, that length, times CIS, cosine plus I sine, of your angle divided by n, or divided by your index. So let's take a look at an example of how to use that. Let's say we wanted to solve the equation x to the 5th plus 32i equals 0 by finding all fifth roots then of negative 32i. Right? We would subtract our 32i over to the right side, and we would want to find all fifth roots of negative 32i. Well, first of all, if we're going to find fifth roots, there should be 5 of them. If you remember answers to polynomials, x to the 5th means I have 5 complex numbers, 5 complex roots. Second thing we want to do is take a look at z equals negative 32i. If we imagine that on a complex plane, we can just drop straight down negative 32 units on the I-axis, which means that r is going to be equal to 32 units, and theta is going to be equal to 270 degrees. Or we could say 3 pi over 2 radians. Well, to find the first root then, we're just going to take the fifth root of 32, cosine plus I sine, that 270 degrees, and instead of multiplying like we did with DeMoivre's theorem before, well, remember, I'm multiplying by the fifth root, so the 1/5 exponent. I'm going to divide by 5. It's just like multiplying by 1/5. So and that will give me my first answer. So we can take a look at it and say fifth root of 32 is 2 cosine plus I sine of 270 divided by 5, which is 54 degrees on there. So there's going to be my first answer. If I went to 54 degrees on my complex plane here, also called an argand diagram, when we're trying to graph these out, I'm going to go to 54 degrees approximately and out 2 units. I'm just going to have this circle with radius 2 here. So this will be out at 2 units there. 54 degrees, there's my first answer. I'm just going to put 1 by it to make that my first solution. Just labeling my axis here. Now, the other question will be, now where are my other 5 roots? Well, remember, all my other roots will evenly divide this circle up into essentially 5 sections. So all the other roots will be, well, 360 degrees divided by 5, which is going to give me a smooth 72 degree angle. So all of my other ones will be 72 degrees apart. So if I want the other 5 roots, the next 5 roots, I'm still going to say 2 times CIS, and I'm just going to do that 4 more times. And now I just need to add 72 onto 54 over and over again. So 54 plus 72 will give me my first one. So 2 CIS, and that comes out to 126 degrees. So I would go to 126, and I can plot this as my second solution. Then if I take 126 and add it again, so plus 72 more degrees, I'm also going to get 198. So again, just a little bit past 180. Add another 72 degrees. So that's 260 makes 270, right on the money. So we'll be right here, the fourth one. And then add it one more time, 72 degrees makes 342 degrees, which would be just short of 360. So there's the fifth of the answers. And if you take a good look at them, again, they're kind of dividing that circle up into even spokes, kind of on a wheel, all 54 degrees apart, or sorry, 72 degrees apart. If you actually add another 72 degrees to 342, you'll actually get 414. But 414, realize, if you accidentally go 1 too far, 414 degrees minus 360 just comes back out to 54 degrees again. So realize if you went 1 step too far, you're just going back again to this next answer and you would just keep getting those same 5 answers over and over again. Let's try it one more time here, only this time we're going to take a look at an example where, hey, if I know they're evenly spaced around my circle, I could actually just make up a little table to kind of set this thing up. First thing I'm going to look at is that the find all fourth roots of 81, well, first of all, 81, if I draw a quick little picture of it, will be directly to the right, 81 units, so r equals 81, and theta will be exactly 0 degrees, because we haven't actually left that positive x-axis. So if I'm finding the fourth roots, fourth root of 81 is just going to be out in front of every one of them. Realize that every single one of my roots, again, is going to be CIS, or cosine plus I sine. But if you notice in the formula up top here, what I'm saying is, if we take theta and we divide by n, just like we did on the last screen, what we're going to do to find the rest of my answers is add on 360 degrees divided by n, or add on, in that last example, that 72-degree angle. But I need to do that multiple times. So what k stands for is which of the answers I'm looking at. The first solution I get, k is actually going to be 0. So 360 times 0 would actually just come out to 0 degrees plus 0 is 0 over 4. And basically, you're going to get 3 CIS 0 degrees, which, if you found those parts, cosine of 0 degrees is 1. So that's 3 in the real numbers. Sine of 0 degrees is 0, so the imaginary number disappears. So we get that 3 in our picture. Then I'm going to do that same exact formula. So fourth root of 81 is 3. And 0 plus 360 times 1 divided by 4 are basically 90 degrees. And remember, if we thought about our 360 degrees divided by 4, 360 over 4, all of my answers really are just going to be 90 degrees apart. Or in my argand diagram, exactly 90 degrees, chopping that into 4 separate pieces. And again, plug in k as 2, I'm going to have 180 degrees, so now I'm going to get my negative 3 over here. Plug in k as 3, you get 270 degrees, still the same fourth root of 81, and I get my negative 3i. And all of a sudden I've got my 4 answers falling nicely on the argand diagram. And again, if you did it 4th time, the reason we don't go k as 4, even though we're doing fourth roots, remember there are only 4 answers. If you did the k as 4, you get right back again, all the way around to this nice 3 in the real numbers. So on the next page, feel free to take whichever approach you like, but go ahead and try to find or solve the solutions here. Take a minute, try it out. I'll post the answers, so pause the video now, and then you'll be able to see the solution. Okay, I've got the solution drawn up for you here in 2 different ways. First of all, up top, we just needed to figure out what we were finding. So my number is root 3 plus I, and I'm finding all the third roots of that number. So first of all, r is going to equal 2, and theta is going to equal pi over 3. We need to make sure we know the trig form of that complex number. On the lower right here in the blue, the first answer, remember, is going to be the third root of my r, or third root of 2, CIS pi over 3 times 1/3. So basically pi over 9. And we get that first answer, k equals 0, down here on the right. Because notice that's also what I would get from my formulaic way of doing this. Third root of 2, CIS, pi over 3 plus 0 times 2 pi, for 0 for k, over 3, which provides me with pi over 9. Then, what I would want to do is, if I'm doing the first way around, my increment, again, is a third of a circle. 2 pi divided by 3 is the same thing as 6 pi over 9. So I'm going to go from 1/9 to 7/9 to 13/9. So I'm just going to keep adding 6 pi over 9 to get my answers. And realize 13 pi over 9 plus another 6 is going to take me right back to pi over 9, or a coterminal angle with pi over 9. In the formulaic way of doing it, again, same thing. Pi over 3 plus 2 pi times 1, all divided by 3, will give you 7 pi over 9. And same thing, 2 pi times 2 plus that, divided by 3, you got your 13 pi over 9. I hope that helps you understanding how to find the roots of a complex number. Again, if you have any questions, please talk to your teacher, and have a great day.